Hello, stat students. Last time we talked about combining random variables and combining normal distributions. Today we're going to talk about a different kind of distribution and a different random variable. It's called a binomial random variable, binomial distributions. When the same chance process is repeated several times, we are often interested in whether a particular outcome does or doesn't happen on each repetition. In some cases, the particular number of repeated trials is fixed in advance, and we are interested in the number of times a particular event called a success occurs. If the trials in these cases are independent and each success has an equal chance of occurring, we have what is called a binomial setting. There are 4 conditions for a binomial setting. A binomial setting arises when we perform several independent trials of the same chance process and record the number of times that a particular outcome occurs. The 4 conditions are, and so we have this idea called bins and something to make note of with that acronym. So B stands for binary. Binary means the possible outcomes of each trial can be classified as success, which is what we want, or failure, which we don't want. So an example could be choosing a student in our class who has an A, that could be a success, and then the failure would be anyone who's not making an A, and that doesn't mean they're failing the class, it's just I'm using this as an example. I means independent. Trials must be independent. That is, knowing the outcome of one trial must not have any effect on the outcome of any other trial. So if I were to give extra credit and choose students, and George got selected to do extra credit, and then he got selected to do extra credit again, that would be independent. All right. So independent means that you are being replaced and you have a chance of being picked again. So if you do not replace, like if you're picking 3 cards if you're picking 3 cards from a deck of cards and you don't replace, you just pick 3, the probability is going to change. So it's dependent. And then the number of trials n of the chance process must be determined in advance. So when I say something like in advance, if you are beginning something and you say we're going to do 10 trials and you don't like some of the results, you can't say, oh, I'm going to change it to 15, or wait, 25 is too many. So it must be fixed in advance. And lastly, S is success. On each trial, the probability P of success must be the same. And we'll do some examples here on the next page. Some definitions. The count X of successes in a binomial setting is a binomial random variable, and our random variables have been capitalized with an X, or with a capital letter, sorry. The probability distribution of X is called a binomial distribution with parameters N and B, where N is the number of trials of the chance process, P is the probability of success on any one trial. So you'd be given a table and you can look at it that way. So you have a binomial random variable, therefore you can have a binomial distribution table as well. The possible values of X are the whole numbers from 0 to n. And the reason why is this is a discrete random variable that you get by counting. So this going back to earlier stuff in our notes. When checking the binomial condition, be sure to check the bins. So check those 4 conditions and make sure you're being asked to count the number of successes in a certain number of trials. So let's take a look at some examples to see if in the following situations, whether the given random variable has a binomial distribution. justify our answer. So we're going to go through the bins. Here's the examples. Example 1. Shuffle a deck of cards. Turn over the top card. Let X equal the number of aces you observe. Put the card back in the deck and shuffle again. Repeat this process 10 times. So let's just write down B-I-N-S. B, binary, stands for success or failure. So our success in this case is getting an ace. Our failure is anything but an ace. So that criteria has been met. For the independence condition, the card is replaced back before the next card is chosen. So the independent condition has been met as well. So the card is replaced. So each choice is independent. N, the number of trials was fixed in advance. It was 10. And lastly, the probability of getting an ace each trial is going to be 4 out of 52. So that's a consistent probability. It does not change. So that condition is met. I'm just going to simplify that. So yes, this will be a binomial distribution. So it satisfies the conditions for a binomial setting. All right. Next one. Choose 3 students at random from your class. Let Y equal the number of students who are over 6 feet tall. Okay. So your success is choosing someone over 6 feet tall. Failure, not over 6 feet tall. I notice you choose the 3 students at random, but it doesn't say anything about replacing the students back. So the same person can't be selected again. So there's no replacement. Therefore, not independent. Because one of the conditions has not been met, it's not binomial. So no, violates independence condition. Right. Flip a coin. If it's heads, you roll a 6-sided die. If it's tails, you roll an 8-sided die. Let W equal the number of 5s you roll. Repeat this process 5 times. Okay, so your success is your W, so the number of 5s you roll. So success equals rolling a 5. Failure is roll anything but a 5. Okay. I, for independence, the coin, notice coins and dice, they don't have a memory. So those are independent. Doesn't remember what was flipped or rolled before. So coin and die have no memory. So those are independent. Number of trials is fixed. You're repeating it 5 times. And as far as success goes, here's where one of the conditions will be violated. If it's a heads, your probability of getting a 5 will be 1 out of 6 because you're rolling a 6-sided die. So that probability is 1/6. You really have to think these things through. The probability will be 1/8 if tails, because it's an 8-sided die and you can only get a 5 1 out of 8 times. So this is violated. So no violates success condition of our binomial setting. So hopefully doing those 3 examples will make more sense. All right, so for any setting in which we are interested in X successes and N trials, P equals, so you have X, you have the X is your binomial random variable, equals X. The little x is the number of successes. So the probability that you get exactly X successes in N trials is equal to the number of arrangements times the probability of success. So basically, we're getting into stuff that you did in Algebra 2, and that is combinations. So the number of ways of arranging, and order doesn't matter in combinations, X successes among N observations is given by what is known as the binomial coefficient. This right here is the binomial coefficient. And it is equal to n factorial over k factorial, or x factorial, sorry. Used to be k back in before the College Board changed it. So x factorial over times n minus x factorial. And this is the same thing. And that is a button you can use on your calculator known as a combination. And I'll tell you the prompts on how to get it on your calculator. Most people just use a calculator because it's faster. And x is equal to 0, 1, 2, all the way up to n, and there's that. So if you wanted to do something like this, if you have, let's see, I am going to give you something like you have 5 trials, and you want exactly 2. What are the ways? How many different ways can you arrange it? So 5, choose 2. And so this is how you would do it. So according to our formula, it would be equal to, this is n, this is x, so it would be 5 factorial, and the bottom would be 2 factorial times 5 minus 2 factorial. And that equals, and factorial is just, here, I'll just write this part. And I know some of you who had Algebra 2 last year and you had to do this 4th quarter on your own, you probably won't remember it. So that's why I'm doing this over again. So 2 factorial times 3 factorial. The bottom 2 numbers must add to equal the top number, but you can't cancel top over the bottom. So that just means 5 factorial means 5 times everything multiplied below it. And the bottom would be 2 times 1 times 3 times 2 times 1. And then you can cancel, and that's the beauty of it. Lots of things cancel. And then you have 20 divided by 2, which is 10. So there's 10 ways, 10 combinations of 2 successes. but most successes, yeah. But most people don't want to do this by hand. It takes too long. So you can do this on your calculator. And how you get to it is you select math first, and then you go all the way to the far right and select probability, PRB, and then you're going to pick the combinations. There's a permutations, there's an NPR, but you want the combinations. But before you do that, depending on the calculator you have, mine's new, so when I go to these three prompts, this is what it'll look like. And there'll be this will be flashing and that will be flashing. And I just put in the numbers. If you have an older calculator, so I would put 5 and 2, and then I would hit enter and it will give me the answer 10. If you have an older calculator, you're going to have to put the 5 first on your main screen and then go to math, probabilities, combinations. And then when you select that, you can then put in your other number. So it's just you can still do it. It's just, one additional step. It's kind of annoying, but you can still do it. So that's the easy way to get the binomial coefficient. Right. The binomial coefficient counts the amount of ways, which I talked about, in which x successes can be arranged among n trials. The binomial probability, the probability x equals x, is the count multiplied by the probability of any one specific arrangement of the x successes. So it's getting a little harder, so you really, really need to focus and pay attention. So for the definition, binomial probability, if x has the binomial distribution with n trials and probability p of success on each trial, the possible values of x are 0, 1, 2, all the way up to n. If x is any one of these values, so I'm going to go over this again. This right here is the binomial coefficient. So here, how do you calculate a binomial probability? So that's what you're being asked here. So the binomial coefficient, to find that, I would use a calculator, obviously. But you take that and you multiply that answer, whatever it is, the number of ways, times p to the k power. So this is going to be the whole thing is going to be your success. Then if p is your success, p to the k power is your success, then 1 minus p to the n minus k is your failure. Right? And so another fancy way of writing the binomial coefficient is that combinations in your calculator times p to the k, times p to the k times 1 minus p to the n minus k. And so check on your formula sheet. This is on your formula sheet. So on formula sheet. So you don't have to worry about memorizing it. Thank goodness. But just know what p and 1 minus p are. You use them in the second semester all the time. So just getting it right now is going to be great. So an example, I will just do one out here to the side. I guess I could do another one. You know what? We're going to do examples on the next page, so we'll just leave it at that. So let's do an example. Examples. Each child of a particular pair of parents has the probability of 0.25 of having blood type O. Suppose the parent have 5 children. So n equals 5. And your probability, p equals 0.25. So you have two things that you really needed to know. Part A, find the probability that exactly 3 of the children have type O blood. So we want to find the probability that exactly, we'll just use the capital X, it doesn't really tell us, exactly 3 children have type O blood. So to set this up, using our binomial probability formula, you have n, remember, is 5. So it's the number of trials. So 5, and you have 3 here, for exactly 3. And I'll label everything for this particular one. So binomial coefficient times your success. So your probability of success is 0.25, and you want exactly 3 children, so that'd be to the third power. That's where you get the exponent. Times, if the success is 0.25, 1 minus, so these two numbers in parentheses have to add up to give you 1. So 0.75 is your failure, and you have 2, because there's a total of 5 children. And then you would just go ahead and use the calculator to multiply everything out. So this is your success for type O, and this is our failure, so not type O. Just labeling all of it one time so it makes sense. And then you would just calculate it in your calculator. So you would go to math, scroll over to probability, and hopefully you have a newer one like I do, the TI-84 plus CE, and then you would just put in, and if you don't, then you do it another way, and then that'll give you some answer, whatever it is, times 0.25 to the third power times 0.75 to the second power. And if you want to work it out old school way and actually do it, then you can do it as that way as well. But this answer is 10. And then you have 0.25 to the third power times 0.75 to the second power. If you do all that, you get 0.08789. And you can definitely leave it as a proportion. You're less likely to make a mistake. If you were to turn it into a percent, just remember to move the decimal point over 2 places. A lot of times students mess up because they can't read their own decimal point in the original problem. So just be very careful. So there is a 8.789% probability that exactly 3 of the children will have type O blood, right? Let's do another one, or let's do part B to add on to us. Should the parents be surprised if more than 3 of their children have type O blood? So if it's going to be more than 3 of the children, so you could have 4 children, exactly 4 children, or exactly 5 children. So probability x equals 4. You have to add those, plus the probability that x, all 5 would have type O blood. So you're going to have to use the binomial coefficient, the binomial probability formula twice there. So you are going to do, for the first one, so your number of trials is 5, and you want exactly 4, times 0.25 to the fourth power, because that's your success, times 0.75 to the first power, plus here, all 5, success, 0.25, all 5, 0.75, 0. Those two exponents should add up to the number to n, right? And then putting this in your calculator would give you 5, and then just 0.25 to the fourth, 0.75. Okay. Here, when those numbers are identical, there's only one way of all 5 having type blood. There's just one way to do that, so it's just going to be 1 times 0.25 to the fifth power. And if you remember your rules of exponents, any non-zero number raised to the 0th power is equal to 1. Right. So did all the left side or all of this right here for your first expression, you get 0.01465. Second one is 0.00098. That gave me, when I added together, 0.0156, or 1.56%. That's very small. So should the parents be surprised? Yes, 1.56% is a very small probability. So yes, the parents should be surprised if more than 3 of their children have type O blood. All right. This would take forever and a year if we were to do it by hand. So there's always a way to do it on our calculator. So let's do an example. When rolling 2 dice, the probability of rolling doubles is 1/6. Suppose that a game player rolls the dice 4 times, hoping to roll doubles. A, find the probability that the player gets doubles twice in 4 attempts. So the probability that the person gets doubles twice in 4 attempts, so x equals 2, exactly 2, would be equal to, here's how you would do it on a calculator, that is. So you would go to a Binomial Pdf, and you use PDF because you have an exact point. So when it's an exact, you use a PDF, but when it's a greater than or less than or greater than or equal to or less than or equal to, you're going to use a cumulative. Now, to get to the Binomial PDF, it's the same place where you go to normal CDF. So you go to second, you go to your distribution menu, and to get that, you press vars, and you scroll all the way down until you see Binomial PDF. And then you will be given prompts, and you're supposed to enter numbers in these prompts. And so the first one is, and it'll say the word trials. And it says that you are going to do this 4 times. So your trials is 4. The P is your probability. So the probability of rolling doubles is 1/6. So just write it as 1/6, 1/6. I wouldn't change it to a decimal because then you're not very accurate when you're rounding. So I would just put it in as a 1/6. And then lastly, x equals 2. So right here is your, let's see. Oh, your player gets doubles twice. So your success is x equals 2. And you let the calculator do it, and you get 0.1157. And that is how you do that one. And it does work when it's an exact value. Now, we get into like a hairy situation when it's not exact, and I will tell you about those situations right now. Where are we going to write this down? You have room to write this down at the bottom of your paper. So over here, here's some calculator prompts. Our calculator only does the exact number. So our calculator does probability when x equals a number. And we used Binomial PDF. So we have trials, probability of success, and the value, the number value from the probability. And we used the PDF because it was an exact point distribution. Okay. Our calculator also does probability when x is less than or equal to a number. It just doesn't do anything that's greater than or equal to, greater than, or less than. So that's where you need to know what to do. So the calculator already does that. So you just need to go in again to Binomial PDF. Oops, sorry, I meant CDF because it's not an exact point distribution. So there you go. So you go to, this time you would choose the Binomial CDF, the cumulative distribution, and then you would use the same stuff here. Right? And it will give you the answer. Now we get into a situation where, and I am running out of room and I don't want you to go to the next page. So I have room over here, and that's where I'm going to put my information. So and you might have room as well. So if you want to, or put the stuff along the side, right here, if you want. I'm just not going to write over there. All right. So I'm going to write over here where I have room. What happens if it's greater than or equal to a number? Well, here's what happens. You have to, before you even go to the second vars menu, you need to put the 1 here first in your main screen, because you're going to take 1 minus, you're going to do the probability that x is less than or equal to that number, a number minus 1. So that's what's going to go here. And we'll do an example. And the reason why is if you have a number here, you can't put it, you can't have it here as well. So you have to subtract 1 from it. It'd be 1 less. And this is what it would look like. So it'd be 1 minus your binomial. You'd still use CDF because it's not an exact value. It'd be trials, probability of success, and it'd be 1 less than the number value. So number value minus 1. And then what if you have greater than or less than? So if you have greater than, so x is greater than a number, so that number is not included. So if you had something like x is greater than 5, 5 wouldn't be included, but 6, 7, 8, whatever would be included. So here you would do 1 minus the probability. So here you could include the number, whatever that number was. So if it's x is greater than 5, it'd be 1 minus probability x is less than or equal to 5, so the number. And I won't go ahead and put all the trials. It's the same thing. And then lastly, if you have probability x is less than a number, it'd be, oh, I didn't put that, it'd be a binomial CDF. So, okay, so let's just put that we're going to use well, you know to use binomial CDF. Okay, so for this one, I won't make the mistake. So for that one, you would do binomial CDF. For that one, you would do, you would subtract 1. So you would do trials, probability of success. Probably doesn't make any sense right now until we do some examples. And then the number value from the probability minus 1. Let's do some examples and maybe that'll help. There we go. Should the player be surprised if he gets doubles more than twice in 4 attempts? So when we do some examples, I think it'll really make sense. So more than twice means greater than 2. So the probability x is greater than 2 is equal to 1 minus the probability that x is less than or equal to 2. Because if it's greater than 2, it could be 3, 4, or whatever. So you can include that 2 in when you're doing the binomial CDF. So you would enter this in your calculator as put 1 first in your main screen minus, then go to your binomial CDF. And then your number of trials is 4. On a free response question, if you're going to use a calculator, again, remember you have to identify these values. Don't just put 4, 1, 6, 2, tell what they are. P equals 1, 6. And your value here it's going to be 2. You don't put x is less than or equal to 2, but that's what it's referring to. So you're still going to put the number 2 there. So when it gives you that prompt for x, you're not going to go write less than or equal to 2. You're just going to put in the value of 2. Okay, but that's what it is. And it'll give you the answer, and the answer is 0.0162. And so there's a 1.62% chance. And so you should be surprised because, again, very small. Right. Let's do our last example. To introduce her class to binomial distributions, Mrs. Desai gives a 10-item multiple choice quiz. The catch is students must simply guess an answer, and the choices are A through E. So that's 5 choices for each question. Mrs. Desai uses her computer's random number generator to produce the answer key so that each possible answer has an equal chance to be chosen. Patty is one of the students in this class. Let X equal the number of Patty's correct guesses. Show that X is a binomial random variable. So basically we're putting all of this together that we learned today. So, all right. So for binary, the success is that she correctly guesses. And the failure is an incorrect answer. Okay. As far as the independent condition, it's a random, whenever things are done randomly with a random assignment, that also satisfies the independent condition. There's 10 items, so the trials is 10. And finally, the probability of success, there's 1 correct answer out of 5 choices, so probability of success equals 1/5 or 0.2. Find and interpret the probability that X equals 3. So she gets exactly 3 correct answers, 3 questions correct. So this is an exact value, so you can use the Binomial Pdf. So if you were going to use a calculator, and I will show you on a calculator just how to get to this. I just didn't want to do it in 2 separate videos and just mess it up. So trials equals 10. The probability of success equals 1/5 or 0.2. It's an exact decimal, so we're okay. And X equals 3. And that'll give us an answer of 0.2013. So let's interpret this. There is a 20% chance that Patty will get exactly 3 questions correct. Make sure you say exactly because it was 3. It was given X equals 3. All right, and then our last but not least, to get a passing score on the quiz, a student must guess correctly at least 6 times. Would you be surprised if Patty earned a passing score? Compute an appropriate probability to support your answer. So at least means probability P is greater than or equal to 6. So we have 1 minus the probability X is less than or equal to 5. So if you're including that number 6 here, you cannot include it here. So it's just going to be one less. So that's 1 minus the binomial. And that makes sense too. Like you're getting 6, if you get 6 questions right, that's going to be passing at least, 6, because that's the 60%. So you can have 6, 7, 8, 9, 10. And so it's 1 minus binomial CDF. And since it's not exact, you're using the cumulative. Trials is 10. Probability is 0.2. X equals 5. Right. And I entered that in my calculator and I got 0.00637, which is 0.637% chance of passing. Because it's such a very small percent, yes, we would be surprised if Patty got a passing score. And those are your notes for today. Have a great day, stat students.